First, I want to thank the organizers for inviting me. That's a great opportunity for me to present my research. So I was supposed to give a different talk, but then I thought that this is the ideal occasion to try something more experimental, something new. Of course, it's based on what I'm working on. Right now, I'm having a project in Lugano, Università Svizzera Italiana, on quantum indeterminacy. So a bunch of the stuff I'm going to say are based on stuff I already worked on, but I want to propose like what I call a very bold claim connecting indeterminacy and the problem of the ontology. So I have to thank Tim also because he already said a lot of stuff, introductory stuff about ontology and about also GRW, so I can be quicker on this. Okay, so I wanted to start with something very general. That's the first time I do this, but I think it's a good occasion. I had to think a little bit about what I'm doing in this conference, since there are mathematicians, physicists, there are very diverse audience. So I started also thinking about a little bit what a philosopher could do in this context. So again, very general problem, and of course I don't have an answer to that. But I think we've been noticing that a lot of the traditional problems of philosophy have been kind of assimilated to other sciences. What's what is mind, what is matter. But I think there are still a lot of what I call gray areas of knowledge where it's not even clear what the problem is in the first place and who should be dealing with the problem. And I give some examples. So explanation is clearly one of the problems. We speak about explanation in all the sciences, and we speak about explanation in philosophy, but it's not clear who should who should try to systematize what an explanation is. There are also other issues. Causation is famously one of them. Passage of time is one of them. So we don't even know when we speak about passage if it's a physical phenomenon, if it's a metaphysical phenomenon, if it's something that goes on in our heads, like some people think. So we don't even know what this is about. And I think information probably, I'm not super sure, but some people believe that. And finally, indeterminacy or vagueness. This is clearly a philosophical problem in the sense that we don't even know who should be taking care of it. So what's interesting about this is that if we think about why there is such a huge interest towards quantum mechanics, we can actually have a kind of a similar explanation to the one I just gave. So I think that still today, more than 100 years later, we still don't know exactly what the problem is. This is also why this is potentially what could explain why people are trying to, have views where information plays a crucial role in explaining what's different between quantum theory and classical theories. So we still, kind of trying to understand what exactly the subject matter is here, and this is what makes it, I think, a philosophical problem. So what I want to do today is to say, let's assume that this is not a coincidence. The fact that we don't know what vagueness is, we don't know who should understand what vagueness is. I'll say more about vagueness in a second. And the fact that we don't know how to solve some of the issues of quantum mechanics. Let's suppose that these two, mysteries are somehow connected. So what I want to say is that this is what I call the bold claim, is that there is actually a kind of interesting connection, kind of to some extent a mapping between what you think about indeterminacy, which again I'm going to say what I mean, and what's the best ontology, somewhat in the sense that Tim told you about. What's the best ontology of the theory? This is very, again, all new. So I hope I'm not gonna, make crazy claims. So what I want to do is first to kind of give a list of the various phenomena that, to some extent, falls under the umbrella of what I call indeterminacy. So I'll give you some examples. Then I will focus on my research, actually, that is ontological indeterminacy, what I call ontological indeterminacy, which I'll explain in a second. Then I'll talk about what people mean by quantum indeterminacy, at least in the philosophical community. And then I'll talk about three different ways of finding this quantum indeterminacy. And then I conclude. And in the first section, I will actually try to propose this analogy between the accounts of vagueness and the ontology of the theory. So let's start with a few examples. So these are all, I guess, claims that are true. So the first one is true because there is no king of France. It's indeterminate whether the present king of France is weighs more than 80 kilograms. This seems to be a prima facie true claim. It's indeterminate whether I'm balding. I'm getting there, so I think I'm still not, but it's gonna be indeterminate soon. It's indeterminate whether the cardinality of the continuum is the least uncountable cardinal. This is, at least according to certain view, you can correct me if I'm mistaken. It is indeterminate. There is no fact of the matter. You have to fix other stuff in order to settle this. This sentence is false, has no determinate truth value. This is an instance of a self-referential paradox. This also seems to be true according to some people. It's indeterminate whether there will be a seed battle tomorrow. This is the most famous example from Aristotle. Similarly, the example from the Schrödinger's cat, it's indeterminate whether the radioactive substance will decay. And finally, electrons with determinate momentum have indeterminate position. So the last two examples both comes from quantum mechanics, 7 and 6. 5 and 6 are structurally similar. There is a tense, and they speak about future possibilities. But we tend to think that these two are different because we can think about the sea battle even in a deterministic scenario. While here there seems to be that the reason why the radioactive substance will or will not decay is related to indeterministic dynamic. But still, structurally similar. What I wanted to say is that all of these are similar to some extent. We can use this it is indeterminate that operator, let's call it, and we attach it to this kind of sentence, and we can make sense of it. But the various phenomena that they express are different. So, of course, they're going to be related to some extent, but I think they are at least logically independent, meaning that we can think of one happening while the other are not happening. So first, we can think of vagueness, which is a semantic phenomenon. Again, some properties like being bold are said to be vague. Then we have indeterminism, which again, as Tim explained, this is what I know about how to define determinism is related to the dynamics. So a theory is indeterministic if it doesn't settle doesn't necessitate or settle a unique continuation of the universe. Then there is uncertainty that is clearly an epistemic notion. Indefiniteness, going back to the example of the King of France, they seem to be related to truth. Undecidability, logic, and then there is ontological indeterminacy. What I want to say with this slide is that this one is different from the other one. When I speak of ontological indeterminacy, I try to speak of something that depends on the word, on how the word is, but it's not related to the dynamics. So we can, for instance, imagine, as philosophers do sometimes, we can imagine that there is that God creates just one instant of the word, okay? So there is no dynamic there, but we could still have ontological indeterminacy as related to objects, properties. So again, this indeterminacy does not refer to lack of knowledge, does not refer to semantic indecision, to how our words work, and not even also to the dynamic evolution. So there is this thought in the philosophy of there is no fact of the matter. In the world, there is nothing that the facts that are supposed to settle the truth of certain statements fail to do that. And this is what I call ontological indeterminacy. Okay, so in the history, I'm not gonna read these quotes, but I just wanted to show you that. Do you mind if I steal some water? I just wanted to show that in the history of philosophy, both Western and Eastern tradition, this notion has been taken very seriously. And I gave one example from the Chinese Buddhist tradition and one from Plato. When Plato speaks of the Chora, which is the receptacle of all things, he clearly seems to be thinking that there is no a way to uniquely define what the Cora is, what the property of the Cora is. There are many other examples, of course, but these are two very good, influential examples. There's also one in the Upanishad I recently found, which says, this is not that, this is that, this is nothing but that. So, of course, there is a lot of things to be explained about the tradition, and I'm not an historian, but I just wanted to say that, this notion was there in the history. However, in more recent history, at least philosophical, analytical tradition, there's been quite skepticism toward this notion. This is famously David Lewis, probably the most influential metaphysician of last decades. Okay, let's hope it's not gonna. This is 10. Okay. If I do this. Okay. So he famously says that the only intelligible account of vagueness locates it in representational world, in our language and thoughts. So he believes that there is no ontological indeterminacy. But so, despite the importance of the notion, as I said earlier, all the famous analytic philosophers discredited this notion of ontological indeterminacy. I quote Russell, also famously Lewis, Evans, Dummett, Heller, and so on. What I want to say is that in recent years, in the last couple of decades, there's been quite an interest toward this notion. So we philosophers managed to provide a way to understand what ontological indeterminacy could mean. And basically, I think we managed to do more or less what Lewis did with modality. So Lewis managed to provide a semantic logic for modal statement. And similarly, today we have ways of understanding what ontological indeterminacy means. So I can give you some examples, but I think I'm going to run late, so I'm just going to mention them. There are two broad families of approaches, one what I call modal and the other objective, again, to account for indeterminacy. Very roughly, the modal approach locates indeterminacy in a certain kind of unsettledness. So the idea is that the actual word is unsettled between different options. And the other approach, what I call objective, tries to provide a definition of indeterminate state of affair, indeterminate facts, indeterminate objects, and to distinguish indeterminate facts or state of affairs from determinate ones. And they do so usually by exploiting the properties, certain patterns of property instantiation. Again, details aside, we can come back to that. But what I want to say is that we now have started to take more seriously this idea. But what matters is not whether the notion is consistent, but rather whether we can apply it to the actual word to some extent, whether it describes something of the actual word. And here comes the debate on quantum indeterminacy. So again, very roughly, we all know that microscopic systems to some extent violate what I call the classical supposition of value definiteness. So in classical physics, we don't have that. In quantum physics, objects, entities, system can instantiate properties without a specific value. In standard quantum mechanics, we have this tool, modulo concerns such as those of David Wallace, but we seem to have this tool in standard quantum mechanics that is called the eigenstate and value link, which connects property instantiation and the mathematical formalism. So whenever a physical system has a definite value, it is in an eigenstate. Only when it is in an eigenstate, it has a definite value. But the problem with that is that we can think that first, orthodox quantum mechanics is problematic because we don't have a clear definition of what a measurement is, but also that we could provide different interpretation of the theory that avoid this indeterminacy. So if we look at the main interpretations, again, the ones already quoted by Tim, allegedly the indeterminacy would disappear. And third, this is the third way to resist this. We can even think that determinacy is a desideratum for a physical theory. So in much the same way, this made me think this morning how classical mathematicians reacted to intuitionism, saying mathematics is not but if it's not determinate or precise. So I think you can see similar things in this debate as well. So this is a long quote by Glick, where he basically says that if we take the Bohmian approach, there is no indeterminacy because the particles are not, the positions and momenta are not indeterminate. If we take the Everettian approach, then at the fundamental level, we only have the wave function and there is no indeterminacy there. There could be, emergent indeterminacy. I'll come back to that. And finally, if we take the GRW approach, the flash and the mass density ontology, neither contain fundamental indeterminacy. So again, the idea here also echoed by Chen is that we have realist theories of quantum mechanics, such as Bohm, GRW, and Everett, that make quantum mechanics precise. And in those precise theories, ontic vagueness disappears. So again, there could be some indeterminacy in standard quantum mechanics given the EL, but if we look at the realist approaches, there is none. Okay, so what if I have 7%? What are we at? Okay, in response to that, I just want to mention a few things. So first, this was actually the topic of the talk I was supposed to give. It's unclear whether non-fundamental would mean anything closer to eliminable, right? So even if we have that indeterminacy in those interpretations only affect the derivative ontology, I think this does not give any assurance of the fact that the derivative ontology, whatever it is, could be affected by indeterminacy. So even in both, maybe there is some indeterminacy at the level of derivative ontology. And also, it has already been argued that there is some indeterminacy affecting each of these interpretations. Again, apart from Bohm, there is a paper on Everettian quantum mechanics. And I've argued that in the case of GRW, at least on some interpretations of GRW, there is probably even fundamental indeterminacy. I don't know what to do with the methodological argument suggested by Glick that determinacy is a desideratum. I think this only shows that it could be true that determinacy is a desideratum, but only until the point where we understand what indeterminacy is. I think at that point, which we now better understand what indeterminacy is, I think at that point, it's not clear why determinacy should be a desideratum. Yeah.
We are now. Yeah.
How much time do I have?
Oh, you have lots of time.
Okay, I'm speeding up because I'm super scared that I'm going to.
We have 25 minutes left.
Total. Okay.
You want to charge your laptop or?
This would be great.
Yeah.
I don't know why people ask.
Well, why don't we take 2 minutes? What's a good time? Take 2 minutes.
Yeah. I didn't have to speed that much. Okay. Yeah, I think it's okay. So there's been an accident, and I couldn't find it.
Source.
Wow. Okay. So now I can slow down. It's too late, but okay. So let me just try and sum up a little bit. So what I wanted to say. So I have a lot of time. What I try to argue so far is that first, there are different varieties of indeterminism. Indeterminacy is one of them. What I call ontological indeterminacy is one of them. And while in the recent history of analytic philosophy, there was skepticism toward this notion. Recently, we managed to provide accounts of ontological indeterminacy. This is crucial, of course. I could go into details if you want, but it's a lot of philosophical.
It's changed. So you.
Sorry?
what happens for such a change?
What happened? I think, actually, probably quantum mechanics played a role in this.
It's not really a recent discovery.
What, quantum mechanics?
Mechanics.
Well, you would,
Philosopher just stumbled over it, or?
I think, probably the fact that they realized that they could provide models, semantics and logics for indeterminacy, were in part motivated by realizing that this happens in quantum mechanics, and it doesn't surprise me that it happens a little bit, later. Lewis actually in his 1986. No, it's not on this. It's in well, around the late 80s anyway. He has the preface of the philosophical paper. He claims exactly where the paper I quoted also, where the skepticism towards the notion is mentioned, is that I'm willing to take any lesson from quantum mechanics, but I'm waiting for them to make clear what they're talking about. So this is 86, and of course, it's the same year as speakable and unspeakable. So of course, I'm gonna quote Bell as well. So it's I agree. It's weird that philosophers, some of them, at least metaphysicians, were not as keen to trying to understand the theory. But I think there were also other historical reasons. There was this paper from Gareth Evans, probably 83, 84, which provides an supposedly reductio ad absurdum of metaphysical indeterminacy. So this was very influential. This paper was very influential.
83.
I say 78.
Evans, yes.
I can't remember. Yeah, 78.
Well,
Yeah. Oh, okay, I didn't know that. 78, yeah. 78. So yeah, I think there are various reasons. Evans probably played a role, and also Lewis, immediately wrote a clarification of Evans' paper. Not immediately, but kind of a couple of years later, I think. So there are many reasons why there was, less interest and less attempt. There's been less attempts. Then, gradually we managed to show that there are ways around of Evans' argument. So I think, there are a lot of explanations, basically. So I think quantum mechanics again played a role, and today it's still, I think, probably the main motivation for taking seriously these weird semantics and these weird metaphysics of ontological indeterminacy. At least to me, I think looking at quantum mechanics is the main motivation.
Could you maximize the window again? Yeah.
Oh yeah, sure. Okay, so as I said earlier, what I want to suggest here is that if we look at the debate on quantum indeterminacy, there's still this kind of argument in favor or against considering indeterminacy in the quantum domain as ontological, or possibly it can be reduced to a semantic indecision or to merely an epistemic phenomenon. So what I want to suggest is that actually, if we look at hidden variables, it looks like they are considering indeterminacy, quantum indeterminacy, as merely an epistemic phenomenon. If we look at forms of wave function realism, of course, Everett and quantum mechanics is one of those. It looks like indeterminacy is considered a semantic phenomenon, because the wave function at the fundamental level is perfectly determinate. Wallace says that the three-dimensional objects are only patterns of the wave function. So if there is some indeterminacy at some kind of meta level, three-dimensional objects are determinate, fundamental wave function is also determinate. If there is an indeterminate at some meso level as affecting, for instance, electrons, this can be explained away linguistically as something that does not refer clearly to anything real. And I think Wallace would go this way. And finally, which is what I'm going to focus on for the last 10 minutes, I want to show that standard collapse interpretation and spontaneous collapse interpretation should kind of lead us to the acceptance of ontological indeterminacy. So I don't think the argument for the first claim, hidden variable epistemic indeterminacy, should be motivated too much. I think it's rather straightforward. As I said, for Bohmian mechanics, there is no ontological indeterminacy. It's just we don't know the positions of the particle, but they are there. As I said, the argument for the link between wave function realism and linguistic semantic indeterminacy is going to be more complicated, but I think there is a lot of textual evidence to show that they seem to think that, they seem to believe that any indeterminacy would be representational, would just affect our language. Recently, Alastair Wilson explicitly tackles this issue of semantic indeterminacy with respect to variety in quantum mechanics. I think the hardest argument is the one related to C. So whether collapse interpretation, both of the standard kind and of the spontaneous kind, actually lead to accepting ontological indeterminacy. There are two issues to believe that. The taste problem, what is known in the literature as taste problem, and the non-accessible mass problem. So I now have to, how much time? 5?
You have 18 minutes.
18?
Including questions.
Including questions, cool. So I don't have to introduce again spontaneous collapse models. These were developed in the late 80s and 90s. Nicola also contributed. The most famous paper is the one from 1986, again, already falsified. Modifications, the idea is that we modified the Schrödinger's equation by adding a stochastic and a nonlinear element. Tim said that. The idea is that we want to explain collapse without, without mentioning any measurement or any observer, because these are ill-defined. Again, we multiply the wave function by a Gaussian, and the Gaussian, as Tim said, is going to localize the state. So we have wave function describing mass being at region A, region B. This wave function is going to, the Gaussian is going to multiply the wave function, and we're going to end up with a state of matter either in A or in B randomly. So because the new equation is stochastic. What is crucial is that the post-collapse state, it's not actually an eigenstate. So the post-collapse state is described by this Gaussian function that has states that stretch to infinities in both sides. Even if it's a very tiny, portion of the Gaussian, still these are states that stretch to infinity. So one could argue that a very small portion of the post-collapse state is actually spread all over three-dimensional space. That's a problem. And also, it's clear that the standard eigenstate eigenvalue link I very quickly introduced earlier, linking eigenstate and definite value property won't work because we don't have eigenstate here. So we have to revise this link. The fuzzy link is the proposal by Albert and Lower from '96, I think. And they argue that we can provide a purely pragmatic revision. We can just assume that properties can be assigned a definite value if the eigenstate is close to 1 given a certain parameter. This is a purely pragmatic way out of the problem, and even Girardi didn't seem to like this purely operational way out. There is a more ontological, let's say, proposal. I think Roderick Tumulka made very clear that the solution to the taste problem should be given by the ontology itself, so not by what we can know or what we can do. And it's very easy to imagine that the fuzzy link is in a way kind of going back to the problem of the measurement problem in the first place, because we are talking about what we can detect, what we can know. A more ontological solution is to simply take at face value what I call the degree, take at face value the quantum state, and basically ascribe properties by degree based on the quantum states. A physical system has a value v of an observable to the extent of the square projection of each state onto the eigenstate of O. Of course, it's going to be huge, but there are still, a small degrees of property that is not, suppose, I found spin up. There is still a very, very small degree of property of being spin down. This, comes with an ontology of properties that come in degree. You can think it's crazy, but it's a. Look at this. This is the philosophical jargon of explaining what this ontology should look like. But basically, I think this should lead us to accept some ontology, some degree ontology, or we can solve the Thales problem in this for a practical purpose way. This is the first argument for thinking that there is some indeterminacy. Either we go pragmatic, as Albert and Lower argue, or we accept something like the degree league. Secondly, this is the only slide with fewer questions. The B-ables problem was actually very important for Girardi and collaborators as well. And already in 1995, with Grassi and Benatti, they wrote a paper trying to modify the first proposal by adding what they call a mass density operator. And this is in part, it also has to do with physical reasons, but it's in part to address the concern of finding an ontology for the theory, B-ables for the theory. So the mass density operator is defined starting with the operators of the number of particles, which was the operator over which the collapse occurred in the first proposal. So collapses occur on the mass density operator. Thanks to the mass density operator, they define what they call the mass density function, which defines, basically gives a field of mass distributed all over space. And this is the ontology of this approach, called the mass density approach to GRW. So I'm sorry I have to go super quick on this, but we can come back to that. So there is quite forgotten argument that shows that actually, and it was already in the paper from 95, that shows that this mass density function is a many-to-one mapping, and that we can actually describe, we can have two mass density functions that describe two very different states. One is a tensor product of, suppose, all half of a certain number of particles being in region A and half of certain particle being in region B, or a superposition of being all in A or all in B. The problem is that the mass density function, of course, won't recognize the difference, and we want, however, to distinguish these two cases from, for physical reasons. Bradley Monton, I think in 2002, provides an example. You can think to send a test particle in between the two regions that is going to be deflected in one case and not undeflected in the other. That's important because in recent literature, it's been argued, especially in the literature on the topic of primitive ontology, it's been argued that the mass density approach to GRW, it's indeterminacy free. There is no indeterminacy in the mass density approach to GRW. And I think there are good reasons to believe that there is still some indeterminacy left. And this is the main reason to believe so. So I wanted to just end up by quoting John Bell. Here is speaking exactly about GRW. And I think it's kind of close to this idea that in GRW, we actually have indeterminacy. At least that's how I read it. It says this mathematics, GRW, would allow electrons to enjoy the cloudiness of waves. So the electrons can, be fuzzy in a way, while allowing tables and chairs, so ourselves, the world we live in, to be rather definitely in one place. And the fact that I think electrons are indefinite is, a good hint is that he used definitely, to distinguish the cloudiness of electron from the three-dimensional world. So I think he would agree that there is some indeterminacy in this approach, which is not what in the recent literature you'll find. So to wrap up, that's the conclusions. Sorry, it was very quick. So the first one is that as I said, there are arguments, one based on the Thales problem and the solutions of it, and the other based on the non-accessible mass problem. That seems to show that we should accept some indeterminacy, at least for some approaches to GRW. So if we accept that there is collapse, probably we will end up to some extent to accept indeterminacy. Secondly, I think this suggests that while most people, at least in the literature on quantum indeterminacy up until today, try to check whether quantum indeterminacy per se is epistemic, linguistic, or ontological, I think we should rather look at each approach separately and possibly try to distinguish between them. And my suggestion, as I said, which was not completely argued for, I argued just for the hardest part, what I call the hardest part. But my suggestion is that a certain attitude towards what indeterminacy, quantum indeterminacy is, will determine and will be determined by your favorite approach to the ontology. If you think that hidden variables is the best approach, you'll end up thinking that epistemic indeterminacy is quantum indeterminacy. And for wave function realism, you're gonna solve it linguistically. And finally, for GRW, probably you'll have to accept that there is ontological indeterminacy. Okay, I'm done. Thank you.
And we do have 7 or 8 minutes for questions.
So, I mean, I'm not sure how well people are going to be able to follow this, but I'm going to ask you a question which you'll understand. So in the GRW theory, when they originally wrote the paper, they just gave the dynamics for the wave. And then when Bell writes about the paper,
He does just density matrix.
so the density matrix. And when Bell writes about it, then he introduces this flash ontology because he says we need some local beables, right? We need what Shelley Goldstein calls a decoration of space-time. And we just saw these images of galaxies and strings, and that's a decoration of space-time, right? You have some localized stuff distributed in some way on space-time. And Bell asked a question which they didn't ask in the original paper and sort of very modestly proposed this flash ontology, which was associated with the collapses, but would give you a precise distribution of these things in space-time. And then the mass ontology thing was developed to give you a different local ontology of something more like a mass density spread throughout space-time, but that's determined. Now, I'm trying to understand when you say there's still indeterminacy in the theory. I'm not quite sure why. Let me just make 2 comments. One is that there's a bunch of argumentation that goes through the eigenvalue, eigenstate link, as you say, and the Tales of Schrodinger's cat paper is about that doesn't fit GRW. But the response to that is to throw away the eigenvalue, eigenstate link, to throw away even any mention of observables as Hermitian operators, right? And Bell says that. He says, look, we have no use for Hermitian operators anymore. The theory is just, the quantum state and the local beables given by these equations. I don't need to have. So that indeterminacy, the one that David and Barry were worried about, was really driven by trying to hang on to some of the classical, some of the von Neumann-ish stuff that really just should get thrown out in favor of the ontology. And then the other thing you said is that, if I understood correctly, you could write down different wave functions which by the mass density projection project to the same distribution of mass. And I'm not sure why that's indeterminacy. I mean, it's true, it means if I only gave you the mass density, you couldn't recover the quantum state, but nobody ever thought you could. I mean, nobody ever thought that just looking at the mass density or the flash thing, there would be a unique association of that with the quantum state.
Definitely right.
So I'm not sure what's the indeterminacy you have left.
No, I think okay, I start with the second part. Of course, if you look at it that way, there would be no indeterminacy. The problem is that if you start from the side of suppose you make an experiment of certain kind of distribution of mass, and you see that a particle gets deflected.
Mm-hmm.
So it means that there was some collapse, going on because there was enough mass, enough, stuff to produce a collapse. And so now I know retrospectively that if there was a collapse, there was a superposition of mass in the first place. And the description of these two regions is the same. I would give the wave function I attach to these two regions is the same I would attach to a region where I have two half of the mass in region A and half of the mass in region B. So the point is, I think this is
the other way around. It's not the wave functions are the same. The two wave functions you just gave me are different.
the mass density
One over
function.
root 2 all over here plus 1 over root 2 all over there is different than.
But
This is-
the mass density function is different. Should be different. The distribution of mass should be different in the two cases, right? It seems that in one case you have a superposition. No, it's like the way I think Nibel, when speaking about this, says, I mean, something you want to call mass if it doesn't behave like mass. I mean, it should not be called mass. In this case, and you see, this is not the mass that should behave as mass in the case of, mass distributed in the two regions equally, right? So the problem you face is whether or not the superposition state of mass that Bassi-Ghirardi called non-accessible, which is also weirdly epistemic as a notion. This mass that is not accessible should be, ontologically, accounted for. Or if you just say, okay, I don't have to make an ontology of what is not accessible. I think even Ghirardi and Bassi recognize that this is, that there is a difference in the ontology. They just say that as long as it's not accessible, we don't have to.
Yeah. Giancarlo had a funny. Anyway, okay, we'll just leave it there.
No,
We can talk about this later.
yeah, I mean, I'm still, trying to. But I think so far I'm pretty sure that in order to understand the difference between the states, we have to account for them in terms of the primitive of the ontology. And if the ontology does not allow for superpositions of mass as primitive ontologies would avoid, which primitive ontologies would avoid, then I cannot explain the difference between the two cases. This is my conclusion so far, but maybe you'll convince me at dinner that I'm wrong. And yeah, that was the first point, but I forgot. We can. Thank you. Thank you.